Hello, I'm Karina Kimani Stewart, a rising senior at Texas Tech University. I study physics with a concentration in astrophysics, and over the last 10 weeks, I was fortunate enough to be part of the University of Florida Astronomy Research Experience for Undergraduates program, working with Dr. Jason Dittman. For this study, we focused on exoplanet HD 209458b, and by exoplanet I mean a planet that does not orbit our Sun. This planet is known to transit or sweep in front of its star. This produces a transmission spectrum that has been known to contain water absorption lines. We wanted to see these water absorption lines using the CRIRES Plus spectrograph, the upgraded version of CRIRES. But this is a new instrument, and with a new instrument comes a new data reduction pipeline. So this summer, our goal was to understand this new instrument well enough to make a data reduction pipeline so that we can locate these water absorption lines. Before we can begin, though, there are a few obstacles to consider. As I mentioned, we are analyzing transmission spectra, meaning that we aren't only detecting the planet's atmosphere, we're detecting the planet's atmosphere embedded in the signal of the star it sweeps in front of. This means we need to dig the planet's atmosphere out of the signal of the star, make a data reduction process, and execute each step exactly for this to work. This is a tall order, but here's how we approached it. We first began by creating a set of calibration frames to help us understand how external factors affected the data. Once those are applied, we subtract the background signal using nodding background subtraction, but more on that in a moment. Finally, we are able to extract the spectra to plot for analysis. We know that to get the planet's atmosphere, we need the signal of the star, but the signal of the star comes with background signal. So we need to detect and subtract this background signal. This is where the nodding background subtraction technique comes in. If this rectangle were our detector, we could place the detector such that we observe this star in this blue shaded region. This gives us the signal of the star plus the signal of the background, and that's what we see in these lighter stripes. If we move the detector and observe in the same region, we can detect the background where the star once was. We move between these two positions multiple times during our observation, creating a nodding effect. This is how we can obtain just the background signal so that we can subtract it from the star signal. What we see here is one of hundreds of spectra resulting from this process. While there are features of the spectrum that mimic what we expect to see, further investigation is needed to confirm our findings. I'd like to take this time to thank the University of Florida Department of Astronomy, the Summer Undergraduates Research at Florida program, and the National Science Foundation for their support and contributions to the success of this program.